You were there for a second. Sure. Well, they play with that. Absolutely. Okay, good morning, everybody. So let's start the morning session of the last day of the conference. So the first speaker of this morning session is Katherine Maxwell from Public IPMU, and the title of lecture is the Neveu-Schwarz group and application to superstring theory. Please start.
So thank you for playing this conference. So this is my work motivated by superstring theory, and in particular, I want to describe how the mathematical construction of this Neveu-Schwarz group comes into play into these equations. And so before I can get to this construction in particular, the motivations should be described in some sense. So superstring theory, I can't explain it to physicists, right? But the idea is, of course, looking at these strings, and so you're led naturally to Riemann surfaces. And so in superstring theory, we are motivated by super Riemann surfaces. So I will start there and then get into these details. So this shorthand for super Riemann surfaces. Okay, so a super Riemann surface is a 1/1 dimensional, it's complex dimension. Supermanifold. So you can define these in your preferred category. I'll say supermanifold here for simplicity. And this is already a super object, but we require another condition. It has a maximally so there's some maximally non-equal distribution D with rank 0, 1. So the condition is that the natural V bracket applied to this distribution gives an isomorphism with quotient by this distribution. So that's the non-integrability condition. And so locally, this looks like it has a generator of the form given by this, where we say Z and zeta are local superconformal coordinates. So this is the concise definition. I should say, those who are not familiar with the idea of supergeometry, this base definition just means we have some decomposition, let's say, or a structure sheaf into an even and odd part, where the even and oddness is giving the sign that could be supercommutativity. So where we take the parity with the symbol, and so the odd function's anti-commute, the even function's commute. So locally we have some identification with, we're working in the complex setting, functions on, say, n-dimensional complex space with some graphs for whatever size gives the super dimension here. So the super geometrical spaces can get quite complicated, and certainly this is a local condition. So the super surface may seem simple, it causes some issues.
So D is a subsheaf of what? Of tangent?
Tangent. So this is it's a super geometrical space with a supersymmetry condition.
D is a subsheaf of T, 0, 1.
Yes. So tangent sheaf here is rank 1/1, and then D is a subsheaf of rank 0.
Stupid question. So why we cannot distinguish just distinguish it as anti-symmetric part of the tangent bundle?
That's what she does. That's what she does. She says, well, 0 plus
I don't know about D.
So you can do decomposition like that to break it into coordinates. Have conditions. We don't make the requirement globally. There's some. Of course, you can decompose locally. Globally, there could be issues. There's different ways to decompose locally. Here, but yeah, so any super geometrical space you can reduce down to a classical geometrical space, but there's different ways to do that.
Is decomposed globally, right?
Yes, this.
But tangent is not.
It's when you get into these other objects, this. Suppose, you know, if you can write this one locally, it's not so bad. The sheaf we're going to be concerned with, some of our analysis of this is, let's say, the sheaf of superconformal vector fields. And these are given by preservation of this D. And unfortunately, this is not locally free. As a sub, it's a subsheaf of the tangent. So it's not as. And this gives the deformations for the moduli space. So when you put all this together, you look at these deformations, your moduli space has dimension of a superspace itself. So there ends up being these odd moduli associated to this space. But you can say for genus greater than 2, it's a superset. What we'll need is a larger moduli space, which also know this. So I have motivation to consider an infinite dimensional version of this moduli space. And so to do this, if we let our my capital sigma is super Riemann surface, we want to consider puncture on this space with formal coordinates function. So using your natural intuition about what a puncture should be, that's what I want here. In supergeometry, we call this a Neveu-Schwarz function, which could be chosen by simply taking your family superhuman surfaces. That's enough to define Schwarz function. And why do we want to consider this now, say, infinity/infinity dimensional space? To every triple we can associate this vector space. So, what we've done is taken this information, allowed poles that are kosher, chosen a particular line bundle, and look sections. So this particular line bundle is the line bundle that gives J-half differentials on our superhuman surface. It's a line bundle associated to these homomorphic differentials. So we write this because now we're working with superhuman surfaces of dimension 1/1. So our differentials have rank, the sheaf has rank 1, 1. We wish to consider a line bundle, and by taking this Berezinian construction of the sheaf, we end up with a line bundle of rank 0, 1. Berezinian just being the super determinant. And so this map leave us behind one side greater than 1. And this space is enough to characterize this information if we consider it within this topological vector space. Which we can do this identification as a subset using the, and so this generator locally generates this. That's what bracket notation is. So we wish to
Set is 0, 1. Meaning that which is square is 0. But this comment is that this the summing is 0, 1, right?
yes.
Meaning
So it's yeah.
This square is an even line bundle.
It's
It's not 0. It's not square.
So if you look at this statement, this is a statement, say, on points in our moduli space. So this is a particular point within our super moduli space here. Unfortunately, since we're working with super objects, working with points is not sufficient. So we went to, let's say, super points or some sort of functorial statement. And so this can be integrated to the transition.
I'm not sure it's visible from. Okay.
This is what will define for us a good map. Infinite dimensional supermoduli space, and what I'll define next as our supergraph. So this I'm doing here just as Grassmannian based off of the J-half differentials. Call this a superset Grassmannian. And it's based off of this topological vector space. So these are formal super Laurent series. And our Grassmannian is given by functor of points, sending S, which could be say a super scheme in general, to become discrete submodules, topological space for J-half differentials completed by this OS given by your super scheme S. So what do I mean by discrete? I mean some, say L, which I denote by this use just that this condition holds locally and this need to hold locally. This natural isomorphism, including into this vector space here, where this H plus is given by the positive disease. Yeah. This map must be freehold. So it could be an isomorphism, but it could also differ by some finite amount to be an isomorphism. And so whatever the Fredholm index of this is, so let's say in dimensional, these parameterize connecting components. So this is already infinite dimensional, and we have Z2 connecting. So it's a large space. So this is maybe the geometrical construction or setting of these objects. And now I want to talk about this super-Mumford form. So the super-Mumford form is an object which originates from this moduli space of curves. And one interesting question is what other forms exist of this type of isomorphism, and can we extend it to larger spaces? So this is what I extending, let's say, isomorphism moduli space via this Christopher map to the spine. So in general, you can make this sort of statement for any value of j for your j differentials. This isomorphism between your line level lambda j over 2 defined as this derived push forward sheaf of the j differentials on your curve. And so we've taken the Arizonian here as well. This is again this Arizonian of
Relation is lambda j over 2.
yes, to match the j half difference. I mean from the geometry. And so you can do this for any j. The line of interest for superstring theory is for any here. And so we are concerned mostly with the 3-half differentials. And by and distinct, you see this 5 coming out, which gives 2 dimensions. So this is one way to derive that. And then under this isomorphism, we have this measure used in superstring theory given by the image under this isomorphism with the structure sheaf, the constant function 1. You can identify a trivializing form over here, and this is what we call a super. So it's a very canonical.
It's a
section of this slide. And this is what you derive from measuring superstring theory. This is motivation. So does an analogous statement hold for this now super Grassmannian, which contains this moduli space? And if you attempt to do this naively, you can quickly see things go wrong. So you can't just make a statement like this. You have to restrict in some way. One particular attempt was by Schwarz in '89. So this is one say is making the least amount of conditions to extend this. And so the main restriction is that we consider some subset within this Grassmannian. Don't call curly U. And it's that under this natural duality on the Grassmannian, given by this natural pairing between forms, we want that duality to also be given by this multiplication by some invertible element here. And so what I'll describe a bit later is this condition could be Heisenberg. Now, just consider some invertible element, and if we make this condition, then
So have you explained what is H is one of the spaces there? What is H of S is?
so it's a similar condition to what I've written here in terms of the different compartments. It's taking this vector space and then
Oh, okay.
this.
Oh, okay. Yeah. So S is just an auxiliary thing.
Yeah.
Okay.
But it's to be precise with the super. Okay. So the formula is let's say dependent on this G and L. G satisfying this of. So this fraction of, say, 4 objects here, which could be simplified if you prefer into this. And what I mean here is each of these is a super tau function. So we can say tau G is given by the section defined by this Berezinian of this map. So G gives an action on our super Grassmannian space. It can move these L's around as I'm hinting at here. If we look at this action in some generality, and we look at the corresponding section coming from this, this is what we call the super tau function, and we should say Schwarz's super tau function. So with the condition imposed on L, you can see here that this is actually L perp. And then this object can be identified as a section of particular combination of
This U is sort of super scheme or subspace in this.
Yeah, something like that.
How big is U? Is it open? Is it closed? Is it finite dimensional? Is it?
It's
How should we think about
it's not it's I'm not sure if I can say its dimensionality precisely, but yeah, it's some pretty much dimensional space. We're cutting it down. We still have some things that we'll figure.
I think in dimension of the whole day. Is it half dimension?
I think that somewhat. So it's still a large modularized space, and so part of what Schwarz proposed when he was proposing this formula was that this U would be a universal moduli space, say superstring theory. And if we look at this condition here, we can start to see if this matches with the usually defined super-Mumford form. But it wasn't particularly clear to me that this was, let's say, a good object for. But we could identify, let's say, we want an object within this line bundle. If we start looking at this, then what we want to identify is j equals to 0. And then this becomes 3 halves and 0 halves. And these Berzinian line bundles over this Grassmannian can be seen to restrict to the lambda line bundles over the moduli space. Here, I guess this is clear, and 3 halves will restrict to this quite nicely. This 0 half Berzinian line bundle would restrict to lambda 0 halves, but we have a duality between the two, so that matches well. So let me spend some time defining this group, and then I can describe how it's applicable to this. So Neveu-Schwarz algebra is what you may be familiar with. So let me write down these relations just so we're on the same page. The L generators form the classical, so there's nothing super in that line here. Classical Beer-Served algebra, the central extension, and then the G generators are giving this Neveu-Schwarz extension. So the one motivation for looking at the form of Neveu-Schwarz group is to generalize this algebra. So if you might, let's say, even look at a Virasoro that which is complex, we know that this doesn't exist. So if we want to do the same with super case, it doesn't exist for the same reason. And so the best we can do is look. So to define this object, first we need to define a super width group. And by this I mean the non-centrally extended strings. This as a functor from superstrings over C to this.
Super.
And super. So we want to take now the S, which is a super scheme, to automotisms. This ring of formal Laurent series. So by R, I mean this statement, right? Is this completion of our vector space from before, R being our sections on S. Now, if we just took normal systems of this as an R, we wouldn't actually end up with the correct object because it doesn't capture the supersymmetry. So the supersymmetry I was writing on the surfaces should be included here. So this is what I do with this S. That they're say super conformal. And by that I mean they preserve the D as before.
When I say it's not visible from the file, I mean the size of the letters. The size of the letters are not visible.
So I think, yeah, this is kind of the main condition there.
Canonical. Zero. Is it canonical?
The D.
Well, I should reserve the sort of the subspace generated by such stuff, not this thing by itself, but yeah.
So
Infinite dimension space. Infinite dimension.
if this is our homomorphism D, just rescale.
Actually, reserve the left ID generated by
The condition of the super conformality can be rewritten like this. If we do let's say a change of coordinates to data, which can be summarized like this. Where we put conditions on these four functions of Z. And the conditions. So this is perhaps not the easiest pair of equations to work with, because we have this derivative and square contributing. Eta and omega here are odd. So these will be nilpotent. The u and v are even functions, and so these are not. So this part may fill out in certain applications, but the main statement here is this u prime goes as this v squared. So we have some double cover type of relationship stated here. And so to give some geometrical structure to this super width group, we can relate it to the more basic structure, which was this Heisenberg group. So using these statements, let's say map the Z hat data patterns to the information contained in U and eta. This is part of this information, but this is now a super from Laurent series, and it will be invertible, and so this lands in the space which we could identify with this part of called a super Heisenberg. So again, it's accurate to just say the invertible elements within this topological vector space, but valued in, let's say, super points S. But I can also write it out in some detail. First, so functions split like this with certain powers of Z. Where we have the condition AN is invertible. And for all ANs less than this N, we're valuing them as nil radical. So this part of these negative powers of Z valued in the nil radical is capturing the superstructure greatly. And this is the part which is giving the structure of the formalness of this group. Without these nilpotent elements, we're looking at just some. And this group would be something like the group of symmetric group of annuli. So this is a extension of this. So if we look at the particular values for N and J here, we can identify this as a panoramically double.
This is something specific only for the super case, right? So this gamma.
This is completely super, yeah.
So this gamma is what's called the like version of one-dimensional Kac-Moody group. So its non-super analog would be the multiplicative group over the field of Laurent series. Yeah, so this is a version of this. And now you say that if you do super version, then, or miracle, it is related to the width group. Well, in the odd case, there is no such connection at all, as I understand. Yes, yes, yes.
Right. Could make some sort of statement. It's kind of super conformal condition. You could make some more direct without requiring it to double.
It still exists. Really good.
Yes.
Still does. Yeah.
Okay.
So some of this, see, most of this has a classical count. The few parts which don't are towards this corner here. This has no classical count. While I have this displayed up above, one of the things I wanted to check with this formula was how it behaves under the action of this Neveu-Schwarz group.
Classical situation still have Mumford forms, right? So what doesn't exist?
There's
Illustration.
in the technicalities of what I've written right there, but you can't define the tau functions in enough generality. That's one place which it fails. The other part which fails is guessing what form that should take. So we could try to put together the appropriate number of, let's say, elements here to get in the correct line bundle, but there would be an error term, which you can't represent as a tau function.
It works better in the super situation.
There's some cancellation in the super case. Between the even and odd. When you're taking the, let's say, the bears. Which I fortunately I won't. So with this particular question, if we look at how this Neveu-Schwarz group acts on, let's say, the tau function to begin with, we oh. So after looking at the super width group, we define the Neveu-Schwarz group. So the only part left is the central extension, and this is this was easily defined if we look at how S width, the super width, if we act on the Grassmannian, over this Grassmannian, there exists a natural Berezinian line bundle. And the Neveu-Schwarz group is defined as the natural object acting on this Berezinian line bundle with the natural function. So this defines different central charges depending on the particular values, let's say this Grassmannian. And so if you choose 0, you get the natural central extension, which I forgot. So the co-cycle defined by that comes into play here. So if we look at the action on the tip functions, we end up seeing these co-cycles. So this is some multiplicative function giving this action, and the two cocycle I've denoted here would be, let's say, defined as the cocycle given by that action over there on the delta zero zero differential component. So delta here would be some difference in this so in the Fredholm dimension, but it varies if J is even. I suppose the interesting thing here is this simplifies enough that this action only depends on this delta. And the delta is, let's say, preserved under the action of the G coming from the Heisenberg. So if we want to consider how our Neveu-Schwarz element acts on the Schwarz's Mumford form, we end up getting these factors exactly equal. So that is flip. So we see fairly simple, at least calculation that this extended Mumford is invariant section. And so this is one way to argue that it is a good extension of the usual super Mumford. So I should say the construction of this is not it shouldn't be a complete surprise how this formula was written down. It imitates a bit how this super Mumford form over the moduli space was originally proved. So that was so the original for the super Mumford form 88 Voronov, I believe. But in particular here, the way you constructed the formula imitates a bit how this extended formula is written down. So it's relating the J hat differentials via this action, which is interesting. So I want to say one last topic, and then I think I'll be done. So this is proposing, let's say, using this U as a universal moduli space to use this measure to do these superstring calculations in a naturally super setting. So all the objects here I've used super geometrical objects. I've not reduced anywhere to classical spaces, and this is part of has plagued people trying to do these calculations in the past. And various people have proposed methods for doing some sort of universal moduli space, either related to this Grassmannian or some sort of Virasoro group. We've described here with the Neveu-Schwarz. So this right here, for instance. I don't use others. Somewhat on a different perspective is if we look at the action of in our case, the Neveu-Schwarz group on the moduli space of superhuman services, we can describe moduli space via that uniformization. So in the first case, this could be called a Virasoro uniformization. In the super case, maybe super Virasoro uniformization. But this is interesting connections.
Can you make your letters smaller?
You want smaller?
I think it's impossible.
Let this be for now. I guess what I had to note earlier, my just perhaps shorter notation, but so this as this formal group can be considered as a geometrical space in some sense, with, let's say, this projection. Now, if we consider this parabolic, in some sense, subgroup, where we could identify this infinite dimensional moduli space. And further, there should be some quotient to double quotient, which could be identified with the non-decorated moduli space.
Gamma.
So gamma maybe isn't a good choice, I could say. Okay. But so each of these would be some sort of stabilizer. So here P would be, let's say, the stabilizer of the triple. And so if we look at our moduli space of curves or supercurves as coming from this formal group, this provides a certain perspective, which is maybe one sort of universal moduli space. You could do integrals. Of course, this needs to be transferred into the Neveu-Schwarz version so that you can get at the measure. But in particular, it's interesting because it should be related to what's called universal particular space. So this is now a real geometrical space, whereas what I'm considering up here are complex spaces. However, so and super diffeomorphisms in the super case, right? So if we try to complexify super Pegmiller space, we can't just directly get a complex group. So this was one motivation to look at these formal groups, is they provide complexification of this. And so this universal Pegmiller space received a lot of attention in papers such as Witten 21, its relation to JT gravity and recursion and random matrix models. So analyzing this with respect to JT gravity gives a lot of interesting connections. And so it's a question of what similar things could hold for these complex versions. Superstring. Yes, so I think it's
Thank you very much for that. So is there any question or comments?
To form on the super Grassmannian, is it a volume form? What is it, a volume form on an infinite dimensional space? What kind of object is this? Is it a section of some bundle or is it? Yes.
so it's a section of this.
So it's not a volume form, it's a section of something which becomes a volume form
Right.
after reduction.
So, to actually perform the intervals the physicists are interested in, you need to define the region you're integrating over with regard to the fermionic structure a bit precisely. Once you do that reduction, you end up seeing that this reduces to a volume form.
Okay.
But it's over a particular construction.
Any other question? If it's not the case, let's thank the speaker again. We will resume up to 11:30. 35 minutes break.